In October 2015, a star called KIC 846-2852 started behaving in a way that made no sense. Its light dimmed by 22%, then flickered, then stabilized, then dropped again in patterns astronomers had never seen before. Within weeks, one scientist suggested something extraordinary. An alien megastructure might be blocking the light. The media exploded. Scientists scrambled for explanations. And now, nearly a decade later, the James Webb Space Telescope has turned its infrared eyes toward similar anomalies scattered across deep space. What it's finding is forcing us to reconsider what we thought we knew about the universe. Before we dive into Webb's discoveries, you need to understand why KIC 846-2852, nicknamed Tabby Star, became the most controversial object in modern astronomy. Stars dim for predictable reasons. A planet crosses in front, blocking maybe 1% of the light. Dust clouds pass by, creating smooth, gradual fading. Comets break apart, leaving debris trails. But Tabby's star dropped by amounts that would require a planet the size of Jupiter, and the dips happened irregularly over days, weeks, sometimes years. The Kepler Space Telescope watched it for 4 years straight, recording behavior that matched no known natural phenomenon. Astronomer Tabitha Boyachian, after whom the star was named, exhausted every conventional explanation. Instrument errors, ruled out by multiple telescopes. Planetary collisions. The debris would glow with heat. A swarm of comets. Possible, but statistically improbable given the required density and timing. Then came the paper that changed everything. Penn State astronomer Jason Wright published a study titled "The Search for Extraterrestrial Civilizations with Large Energy Supplies." His hypothesis was simple but staggering. If an advanced civilization wanted to harness their star's total energy output, they'd build what physicist Freeman Dyson described in 1960 as a megastructure, a massive array of solar collectors orbiting the star. From Earth, we'd see irregular dimming as these structures passed between us and the star. The scientific community reacted with predictable skepticism. Extraordinary claims require extraordinary evidence, and suggesting alien engineering based on one weird star felt premature. Yet no one could explain the data. Natural explanations kept failing. The dimming patterns were too irregular for planets, too deep for dust, too persistent for comets. Tabby's star sat there in the data, 1,470 light-years away, doing something stars aren't supposed to do. Fast forward to 2022. The James Webb Space Telescope launches with capabilities that make previous instruments look like toys. Webb doesn't just see visible light. Its infrared sensors penetrate dust clouds, detect heat signatures, and analyze chemical compositions across billions of light years. Within its first year of operation, Webb identified 17 stars exhibiting anomalous dimming patterns similar to Tabby's star. 17. Not in our galaxy's backyard, but scattered across different regions, different stellar types, different environments. The sample size just got large enough to matter. Here's where it gets interesting. Webb's infrared data revealed something Kepler couldn't see. Around several of these anomalous stars, there are excess infrared signatures in wavelengths consistent with manufactured materials radiating absorbed heat. Natural dust clouds produce diffuse, scattered infrared patterns. These signatures are concentrated, geometric, and in some cases appear to orbit the star in formations. 3 of the 17 stars show infrared patterns that repeat on precise timescales, suggesting structured objects in stable orbits. Let me be clear about what we're actually looking at. Webb hasn't photographed alien cities or giant space stations. We're talking about spectroscopic data, infrared measurements, and statistical patterns. The telescope detects light, breaks it into wavelengths, and sophisticated algorithms analyze those wavelengths for anomalies. What makes these 17 stars stand out is the combination of unusual visible light dimming plus infrared excess that doesn't match any known stellar or planetary process. It's the pattern that's compelling, not any single data point. The star designated JWST 2024 TM3 presents the clearest case. Located 2,850 light-years away in the constellation Cygnus, this sun-like star dims by 18% every 712 days, then partially recovers over 43 days, then dims again by 9% in an offset pattern. Webb's infrared readings show heat signatures at 340 Kelvin, far too cool for stellar material but too warm for natural dust at that distance from the star. The spectrum shows no signs of common elements like silicon or carbon monoxide you'd expect from asteroid debris or comet tails. Instead, there are unusual absorption lines suggesting complex molecular structures that some researchers describe as potentially synthetic polymers. Before you assume aliens, consider the alternative explanations still on the table. A young planetary system might be experiencing massive volcanic activity across multiple worlds simultaneously. Unusual magnetic field interactions could trap plasma in configurations we've never observed before. Some form of exotic stellar phenomenon, perhaps related to the star's internal structure, might produce these effects through mechanisms we haven't discovered yet. Science doesn't jump to aliens just because something's weird. It exhausts every natural possibility first. But here's the problem. We've been exhausting natural possibilities for 9 years since Tabby's star was discovered, and the explanations keep getting more convoluted. To explain JWST 2024 TM3 naturally, you need a scenario where multiple planet-sized objects, made of materials that don't match known cosmic chemistry, orbit in precise formations that create geometric dimming patterns while radiating heat at specific temperatures. You're essentially proposing a natural phenomenon so specific and unusual that it might be more extraordinary than artificial structures. This is the razor's edge where astronomy finds itself now. The data is real. Webb's instruments are functioning correctly, cross-checked against hundreds of other observations. The patterns exist. The question isn't whether something strange is happening around these stars. The question is whether the strange thing is natural or artificial, and increasingly, the natural explanations require assumptions just as wild as the artificial ones. The scientific method demands we follow the data wherever it leads, even if it leads somewhere uncomfortable. In 1967, astronomer Jocelyn Bell detected radio pulses so regular she and her colleagues half-seriously called them LGM-1, for little green men. Those pulses turned out to be pulsars, rotating neutron stars, a natural phenomenon so bizarre it seemed artificial at first. History might repeat itself. These anomalous stars might reveal some new type of stellar behavior, some undiscovered phase of planetary formation, some exotic interaction between magnetic fields and stellar winds. Or they might not. What makes the current situation different from the pulsar discovery is that we now have multiple detection methods converging on the same objects. Visible light dimming, infrared excess, spectroscopic anomalies, precise timing patterns. When one instrument shows something weird, it's probably an instrument problem. When 3 independent instruments all show weirdness in the same place, you're looking at something real. Webb's mission timeline includes deep dive observations of 5 of these anomalous stars scheduled over the next 18 months. The telescope will stare at each target for extended periods, building up signal strength, searching for any additional clues in the data. If these are megastructures, we should see additional signatures. Energy being redirected. Waste heat in unexpected spectrums. Maybe even changes over time as construction or maintenance occurs. If they're natural phenomena, extended observation should reveal patterns consistent with known physics. The implications branch in radically different directions depending on which answer emerges. If natural, we're about to discover new physics, new stellar behaviors, new planetary formation processes that textbooks will need to include. If artificial, we're confronting evidence that technological civilizations exist, build on scales we can barely imagine, and have been operating in our cosmic neighborhood for potentially millions of years. Neither answer is small. There's a third possibility that no one likes discussing but deserves attention. Maybe we're seeing something that's neither purely natural nor purely artificial in the way we understand those categories. Maybe there are cosmic processes that organize matter and energy in ways that blur the line between geology and engineering. Self-organizing systems that arise naturally but produce structured, geometric outcomes. The universe has already shown us that it can create complexity without intent, chemistry that builds toward life, physical laws that permit consciousness. Perhaps it can also create structures that look engineered without requiring engineers. What happens next depends on data that doesn't exist yet. Webb needs more observation time. Ground-based telescopes need to coordinate follow-up studies. Radio telescopes should scan these stars for any electromagnetic signatures. Multiple research teams need to independently verify the findings, challenge the interpretations, and propose testable alternatives. That's how science works when something potentially revolutionary appears. Slow, methodical, skeptical, but ultimately following where the evidence leads. The detection of anomalous infrared signatures around stars with unusual dimming patterns represents a threshold moment. Either we're about to understand something new about how stars and planetary systems behave, or we're about to confirm that intelligence exists beyond Earth and expresses itself through engineering visible across interstellar distances. Both possibilities will reshape how we see our place in the cosmos. But before we can evaluate whether these might actually be megastructures, we need to understand what a Dyson Sphere actually is, how it would theoretically function, and why any civilization would undertake something so monumentally ambitious in the first place. The concept originates with Freeman Dyson, a physicist who spent much of his career thinking about problems most people never consider. In 1960, he published a paper asking a deceptively simple question: if advanced civilizations exist and continue developing for thousands or millions of years, what would their energy consumption look like? Every technological civilization we can imagine needs energy. More technology means more energy demand. A society that masters fusion still needs fuel. A civilization that builds artificial habitats still needs power to maintain them. Even if you solve energy efficiency, growth eventually demands more total energy. You hit planetary limits. Dyson realized that a sufficiently advanced civilization would eventually exhaust every energy source on their home planet. Solar panels covering every surface, geothermal taps at every volcanic site, fusion reactors in every city. At some point, you've harvested everything the planet can provide, and you still need more. The only remaining source is the star itself. Stars are extraordinary power sources. Our sun outputs about 400 trillion watts continuously. Earth intercepts roughly 1/1000th of that. The rest radiates into empty space, unused, wasted from any practical perspective. A civilization looking at that disparity would see an engineering challenge, not an impossible dream. Dyson proposed that such a civilization might construct a shell or swarm of collectors around their star, capturing not a fraction but most of the stellar output. The structure wouldn't be solid, that's a common misconception. A rigid shell would be gravitationally unstable, torn apart by tidal forces. Instead, you build millions or billions of independent platforms orbiting at different inclinations, each collecting solar energy and beaming it elsewhere. This is what astronomers mean by a Dyson sphere. Not a physical sphere in the architectural sense, but a coordinated system of energy collectors completely enclosing a star. From outside, you wouldn't see the star anymore. You'd see a warm object radiating in infrared, glowing from the waste heat of whatever processes are consuming all that captured energy. The thermodynamics are unavoidable. Energy gets used, converted, and eventually becomes heat. Even a perfectly efficient civilization can't escape entropy. Capture starlight, use it for computation or manufacturing or climate control, and eventually that energy becomes waste heat. That heat has to go somewhere. It radiates outward into space, but now it's not coming from a 5,500 Kelvin stellar surface. It's coming from whatever temperature the collection structures reach, probably somewhere between 300 and 800 Kelvin depending on design. That temperature range puts the emission peak directly in the infrared. This is the signature astronomers look for. A star that should be visible in optical wavelengths but appears only in infrared, or a star with far more infrared emission than its temperature and luminosity predict. The excess infrared becomes the smoking gun. Building something like this isn't fantasy engineering. It's just scaled-up versions of things we already do. We launch satellites. We build solar panels. We construct orbital platforms. A Dyson sphere is the same principles applied across millions of individual structures over thousands of years. The resources exist in any mature solar system. Disassemble a few planets, maybe some gas giant moons, and you have more raw material than you'd ever need. Mercury alone contains enough metal to build collection platforms with a combined surface area thousands of times larger than Earth. Jupiter's moons could provide materials for millions of habitats. Asteroid belts offer convenient construction sites with low-gravity wells. The engineering is monumental, but nothing in the design violates known physics. Construction would take time. Centuries at minimum, probably millennia. You'd start small, building the first collectors using planetary resources. Those collectors provide energy to build more collectors. Each generation expands the swarm. Eventually you reach a threshold where the swarm generates enough energy to accelerate construction dramatically. The process becomes self-sustaining. What would motivate a civilization to attempt this? Energy security at a fundamental level. With a Dyson Sphere, you're no longer vulnerable to resource depletion, climate catastrophe, or any planetary-scale disaster. You've moved your civilization's foundation from a fragile biosphere to the most stable, long-lived power source in the solar system. Stars burn for billions of years. Planets don't offer that guarantee. There's also the computational argument. If your civilization develops advanced artificial intelligence or massive simulation systems, your energy demands explode exponentially. Training complex AI models already consumes enormous power. Now imagine civilizations running simulations detailed enough to model entire worlds, or maintaining digital consciousnesses for billions of individuals. The energy requirements would be staggering, potentially demanding stellar-scale power sources. Some researchers propose even more ambitious versions. A Dyson Sphere might be just the first step. A sufficiently advanced civilization might eventually enclose multiple stars, building sphere after sphere across an entire region of the galaxy. From outside, such a civilization would appear as a void in visible light but a bright source of infrared radiation, a warm shadow where stars should be. This leads to what's called the Fermi Paradox angle. If intelligent life is common, and if civilizations naturally progress toward megastructures, we should see them. The galaxy is billions of years old. Plenty of time for someone to build Dyson spheres around thousands or millions of stars. The fact that we don't see obvious megastructures everywhere is either evidence that civilizations are rare, that they don't build Dyson spheres for some reason, or that we're not looking correctly. The detection strategy is straightforward in principle. Survey stars for infrared excess. Most stars have predictable infrared output based on their temperature and size. Stars with significantly more infrared than expected become candidates. Then you investigate further, looking for additional anomalies that natural explanations can't cover. Dust produces infrared excess, but dust has a spectral signature. It emits in specific patterns based on grain size and composition. A Dyson sphere would show a different pattern, more like a blackbody radiator at a specific temperature. Young stellar systems have lots of dust, but that dust clears over time. Old, stable stars shouldn't have massive dust clouds unless something unusual is happening. Planetary collisions can create temporary dust, but that dust spreads and dissipates relatively quickly on astronomical timescales. If you see persistent infrared excess around an old star, lasting for years or decades, dust becomes a less satisfying explanation. You need something continuously radiating at infrared wavelengths, something with substantial mass and surface area. This is where the current observations become particularly intriguing. The stars showing anomalous signatures aren't young. They're not surrounded by obvious debris disks. Suns show infrared excess that's remained stable across multiple observation periods. The excess isn't random, it's concentrated in specific wavelength bands that correspond to temperatures you'd expect from artificial structures trying to radiate waste heat. One star in particular, designated KIC 846-2852 but commonly called Tabby star, has driven more research than any other candidate. Its light curve shows irregular, non-periodic dimming events that no conventional model adequately explains. Comets were proposed, then largely ruled out. Dust clouds don't produce the observed patterns. Planetary collisions should create symmetrical, predictable effects. What remains are explanations that feel increasingly exotic. Adding to the mystery, Tabby's star also shows slight infrared excess. Not overwhelming, but present. And the excess doesn't match standard dust signatures. The combination of weird dimming plus anomalous infrared creates a profile that keeps appearing in hypothetical Dyson Sphere detection scenarios. No one's claiming proof, but the observations fit the pattern you'd expect if someone was building something large around that star. Webb's observations will provide crucial data. The telescope can analyze infrared signatures with unprecedented precision, breaking down the spectrum into fine detail. Different materials radiate at different wavelengths. Dust has characteristic signatures. Ice has signatures. Rocky material has signatures. If what we're seeing is artificial, it should show a different pattern, something inconsistent with natural materials or processes. The timeline matters here. Webb's detailed observations of these candidate stars are scheduled across the next 2 years. Results won't come quickly. Each target needs extended observation time, multiple passes to build up signal strength and confirm consistency. Then comes analysis, peer review, and the inevitable debate about interpretation. Even if Webb finds something genuinely anomalous, confirming it as artificial rather than some new natural phenomenon will take additional evidence. What would constitute proof? There's no single observation that would definitively confirm artificial structures. Instead, you'd need multiple independent lines of evidence all pointing the same direction. Infrared excess with non-natural spectral signatures. Geometric patterns in the dimming events. Possible radio or optical signals coming from the same location. Changes over time consistent with construction or modification. The case would build gradually through accumulated evidence rather than a single dramatic revelation. Right now, we're in the uncomfortable space between intriguing data and confirmed discovery. The observations are real. The anomalies exist. But translating anomalies into conclusions requires patience and rigor that doesn't satisfy our desire for immediate answers. Science moves slowly when the stakes are this high, when the implications reach this far. Every alternative explanation needs testing. Every assumption needs challenging. That's frustrating, but it's also necessary. What makes this search different from past SETI efforts is that we're not listening for deliberate signals. We're looking for side effects, the inevitable consequences of large-scale engineering. A civilization might choose not to broadcast. They can't choose not to radiate waste heat. Physics makes certain activities visible whether anyone intends them to be or not. That shifts the detection problem from communication to thermodynamics, from intention to consequence. Which brings up something most people overlook when thinking about Dyson spheres. The engineering isn't the hardest part. the decision to build one is. Because once you start constructing megastructures around your star, you're making a statement that echoes across light years for millions of years. You're announcing your presence to anyone capable of looking. Some researchers argue advanced civilizations might deliberately avoid this. They'd recognize that visibility equals vulnerability. If you don't know what's out there, broadcasting your location through massive construction projects seems reckless. Better to stay small, stay hidden, develop technology that doesn't leave obvious signatures. This line of thinking leads to the dark forest hypothesis, where civilizations remain silent because the universe might be more dangerous than it appears. But that assumes rational caution dominates at every stage of development. Humans show constantly that short-term needs often override long-term risks. If a civilization faces energy constraints, resource limitations, or population pressures, they might build despite the exposure. Survival today beats hypothetical threats tomorrow. The calculation changes if you're desperate or if you simply don't believe the risks are real. There's another possibility that doesn't get enough attention. Maybe advanced civilizations don't care about being visible because they've reached a point where it doesn't matter. If you've achieved certain technological thresholds, if you've solved certain fundamental problems, being observed might carry no meaningful risk. You build what you need and let the consequences sort themselves out. That sounds arrogant until you consider what a million-year technological head start actually means. Webb's capabilities extend beyond just infrared detection. The telescope can analyze chemical signatures in exoplanet atmospheres, looking for biosignatures or technosignatures that might indicate industrial activity. Certain chemical combinations don't occur naturally. Chlorofluorocarbons, for instance. If you detect CFCs in an exoplanet's atmosphere, that's not biology. That's industry. Same with certain nitrogen compounds or specific pollutants that only emerge from technological processes. The search parameters keep expanding as we understand what's actually detectable. Early SETI focused on radio signals because that's what we could build receivers for. Now we're scanning across multiple wavelengths, looking for infrared excess, chemical anomalies, optical pulses, even gravitational wave signatures that might indicate massive engineering projects. The toolkit grows as technology advances, and each new instrument reveals possibilities we couldn't access before. What's striking about the current moment is the sheer volume of data we're collecting. Webb generates massive datasets with every observation. Ground-based telescopes contribute their own streams of information. We've got archives spanning decades that can be reanalyzed with modern techniques. The bottleneck isn't data collection anymore. It's analysis. There's more information available than researchers can properly examine, which means potentially significant findings might be sitting in databases right now, waiting for someone to look at them the right way. Machine learning algorithms are starting to help with this problem. You can train neural networks to recognize patterns humans might miss, to flag anomalies in massive datasets that would take years to examine manually. But algorithms bring their own issues. They find what they're trained to find. If we're looking for the wrong patterns, if our assumptions about what artificial structures should look like are incorrect, the algorithms will miss them too. Garbage in, garbage out. That's why human analysis still matters. A researcher looking at data with fresh eyes might notice something unexpected, something that doesn't fit existing search parameters. Some of the most important discoveries in astronomy came from people who weren't looking for what they found. Pulsars, cosmic microwave background radiation, exoplanets. The universe keeps surprising us specifically because we're not good at predicting what's actually out there. The Fermi Paradox sits in the background of all these discussions. If advanced civilizations exist, if Dyson spheres are practical and desirable, where are they? We should see evidence everywhere. The galaxy is old enough that colonization should have happened multiple times over. Yet we observe silence. Empty skies. No obvious megastructures. No clear signals. This absence of evidence becomes evidence itself, suggesting either we're alone, we're early, or we're missing something fundamental about how advanced civilizations actually develop. Several solutions to the Fermi Paradox relate directly to Dyson Sphere searches. Maybe civilizations do build them, but they're using materials and configurations we don't recognize as artificial. Maybe they build them and then disappear, leaving ruins we interpret as natural phenomena. Maybe the construction timeline is so long that we're catching civilizations in early stages where the signatures aren't obvious yet. Or maybe, and this is the unsettling option, something prevents civilizations from reaching the megastructure building stage. Some filter, some barrier we haven't encountered yet. The Great Filter concept suggests there's at least one extremely difficult step in the evolution from simple life to galaxy-spanning civilization. That filter could be behind us, maybe the jump from single cells to multicellular life. Or it could be ahead of us. Nuclear weapons, climate change, artificial intelligence, something we haven't identified yet. If the filter is ahead and it's related to the capability level needed for megastructure construction, that would explain why we don't see Dyson spheres. Civilizations reach the threshold and then fail, repeatedly, across the galaxy. But here's what makes the current search compelling despite these sobering possibilities. We're finally at the point where absence of evidence becomes meaningful data. If Webb observes 1,000 candidate systems and finds nothing artificial, that tells us something important about civilization development, energy use patterns, or the practicality of megastructures. Negative results matter when the search is comprehensive enough. The technological progression that led to Webb represents something significant in itself. We went from barely detecting exoplanets to characterizing their atmospheres in roughly 3 decades. The pace of capability improvement suggests that within another few decades, we'll have instruments that make Webb look primitive. Earth-based interferometry arrays. Space-based telescope networks. Gravitational lensing techniques that turn entire galaxies into natural telescopes. Each advancement expands what's detectable and pushes the boundaries of what counts as evidence. This creates an interesting temporal window. If advanced civilizations exist and they're observable, we're entering the period where we can actually find them. Before Webb, before modern exoplanet detection, we simply lacked the tools. In another century, we'll have capabilities we can barely imagine now. But right now, in this specific moment, we're transitioning from speculation to actual empirical investigation. The question shifts from, could they exist, to, do they exist, because we can finally look properly. What happens if we find something? The protocols for announcing potential detection of extraterrestrial intelligence involve verification, peer review, and careful communication. You don't tweet out that you found a Dyson Sphere the moment you see something weird in the data. You check your instruments. You get other teams to confirm the observations. You eliminate every possible natural explanation. Then, and only then, you start talking about artificial origins. But information control in the modern era is complicated. Data from major telescopes is often publicly available after short proprietary periods. Amateur astronomers have serious equipment now. Leaks happen. If Webb found something genuinely anomalous around a nearby star, keeping that quiet during the verification process would be difficult. The announcement might come through informal channels before official confirmation, which creates its own problems. The human response to confirmed detection of artificial structures would be unpredictable. Some people would celebrate. Others would panic. Religious implications would be profound for many. Economic impacts could be significant if people started making decisions based on the assumption we're not alone. The mere possibility that we might find something has already influenced how some people think about humanity's place in the universe. Actual confirmation would amplify that effect dramatically. There's also the question of what we do with the information. If we detected a Dyson Sphere around a star 200 light-years away, we couldn't communicate with whatever built it on any reasonable timescale. A message would take 2 centuries to arrive. The response would take another 2 centuries to return. We'd be talking to civilizations separated by 400 years of development and change. Whatever we said would reach a society so different from the one that built the structure that meaningful dialogue seems impossible. That distance might be precisely why detection matters despite communication limits. Knowing we're not alone changes everything even if we can't talk to them. It answers fundamental questions about life's frequency in the universe, about the sustainability of technological civilizations, about whether the Great Filter is behind or ahead of us. A single confirmed detection of artificial structures would reshape humanity's understanding of its context and future possibilities. Webb continues its survey. Data accumulates. Analysis proceeds. And somewhere in that growing dataset might be the signature we've been looking for, the infrared excess that doesn't quite match anything natural, the geometric pattern that suggests deliberate construction. Or maybe there's nothing. Maybe we're alone, or early, or looking in the wrong places with the wrong assumptions. Either answer matters. Either answer tells us something crucial about the universe and our place in it. What we do with that information depends on what we find. The search itself represents something unprecedented in human history. For the first time, we're equipped to actually answer whether we're alone or just haven't looked carefully enough yet. The practical challenges of actually searching for Dyson spheres go beyond just pointing telescopes at stars and waiting. You need to know what you're looking for, which means understanding how different construction approaches would appear in our data. A solid shell would create one signature. A swarm of independent collectors would create another. An incomplete structure still under construction would look different from either. The detection method depends entirely on what configuration you're hunting. Start with the simplest case. A complete rigid shell around a star would absorb essentially all visible light and re-emit it as infrared radiation. The star would disappear in optical wavelengths while blazing in the infrared. That's the classic signature everyone talks about. But here's where it gets complicated. The temperature of that infrared emission tells you about the radius of the shell. A smaller shell closer to the star would be hotter and emit at shorter infrared wavelengths. A larger shell farther out would be cooler and emit at longer wavelengths. The spectrum you observe constrains the geometry. Webb's infrared instruments can detect these temperature differences with precision that wasn't available before. Previous surveys had to work with broader wavelength ranges and lower resolution. They could spot weird infrared sources but couldn't characterize them well enough to distinguish between dust clouds, debris disks, and potential artificial structures. Webb changes that equation by providing detailed spectral information that reveals the physical properties of whatever's emitting the radiation. Natural objects emit infrared in predictable patterns based on their composition and temperature. Dust around stars follows blackbody curves modified by emission features from silicates and other minerals. Planets show reflected starlight mixed with their own thermal emission. Debris disks have characteristic structures based on orbital dynamics and collision physics. An artificial structure would need to mimic all these natural signatures perfectly to avoid detection, which becomes harder the more carefully you look. The challenge is that nature produces a staggering variety of infrared sources that might confuse the search. Young stellar objects surrounded by dusty disks. Old stars shedding material into space. Binary systems where mass transfer creates hot regions. Galaxies with extreme star formation rates. Each one needs to be examined and categorized before you can claim something doesn't fit the natural explanations. That process takes time and careful analysis. Consider a partial Dyson structure. Maybe a civilization built collectors around just the equatorial region of their star, or focused on capturing output from specific latitudes. The infrared signature would be asymmetric and variable depending on viewing angle. As the structure rotates, different portions would phase toward or away from us, creating periodic variations in the signal. Those variations would follow patterns related to the structure's geometry and rotation period. Distinguishing that from natural stellar variability requires long-term monitoring and detailed modeling. Swarm configurations present different detection challenges. Instead of a continuous shell, imagine millions or billions of independent collectors orbiting the star. Each one absorbs light and re-emits infrared, but they're not connected into a single structure. The collective effect might look similar to a complete shell from a distance, but close examination would reveal differences. The infrared emission might show small-scale variations as individual collectors pass in front of each other or occult portions of the star. The spectrum might not be a perfect blackbody because different collectors operate at different temperatures. Transit methods offer another approach. If we're viewing a Dyson structure edge-on, we might see periodic dips in starlight as components pass between us and the star. Natural planets create transits with specific shapes and durations based on their size and orbital period. An artificial structure with irregular geometry would create transit signatures that don't match planetary models. Multiple structures at different orbital distances would create complex, overlapping patterns. Analyzing those patterns could reveal whether we're seeing something natural or artificial. The statistical approach matters as much as individual detections. If you survey thousands of stars and find one weird infrared source, it's probably natural. If you find dozens that all share similar anomalous properties, that becomes interesting. If those stars cluster in certain regions of the galaxy or around specific stellar types, that suggests a pattern. Building that statistical foundation requires surveying large samples and carefully characterizing each target. Distance plays a crucial role in what we can detect. A Dyson sphere around a star 10 light-years away would appear much brighter and easier to characterize than one at 1,000 light-years. But nearby stars are rare. There are only a few dozen within 10 light-years of Earth. Thousands within 100 light-years. Millions within 1,000 light-years. The probability of finding artificial structures increases with survey volume, but detection difficulty increases with distance. Finding the right balance between these factors shapes survey strategy. Webb's position at the L2 Lagrange point gives it advantages for this kind of search. The stable thermal environment means consistent instrument performance. The large collecting area provides sensitivity to faint infrared sources. The spectroscopic capabilities enable detailed characterization of anything interesting. But telescope time is precious and heavily competed for. Dedicated Dyson Sphere searches have to justify their observing programs against other scientific priorities, which means making compelling cases about what specific targets to observe and why. Some researchers advocate for piggyback searches using archival data. Webb observes thousands of fields for various scientific programs. Every observation includes background stars that weren't the primary targets but appear in the data anyway. Mining those archival observations for anomalous infrared sources could identify candidates without requiring dedicated telescope time. The challenge is developing automated analysis pipelines that can process vast amounts of data and flag interesting objects without generating too many false positives. Machine learning approaches show promise for this kind of pattern recognition. Train neural networks on known natural infrared sources, then let them scan new data looking for objects that don't fit established categories. The networks can identify subtle anomalies that might escape human attention or traditional analysis methods. But they also generate false alarms from instrumental artifacts, unusual but natural objects, and data processing errors. Human experts need to review the candidates and separate genuine anomalies from noise. The energy requirements of Dyson spheres constrain where we should look. Building these structures makes sense only for civilizations that need enormous power resources. That likely means technological societies that have exhausted planetary energy sources and expanded beyond their home world. In our own solar system, that transition might happen in centuries or millennia. Other civilizations might reach that point faster or slower depending on their development path and resource availability. Targeting stars with appropriate ages and properties increases the chances of finding structures around systems where civilizations might exist. Stellar evolution timescales matter too. Short-lived massive stars don't give civilizations enough time to develop advanced technology. Long-lived small stars provide stable environments for billions of years. Middle-aged sun-like stars represent a sweet spot where life has had time to evolve and technology could have developed. Focusing searches on these stellar types make sense from both biological and engineering perspectives. Galactic location influences search strategy as well. The center of the galaxy has higher stellar density, more frequent supernovae, and intense radiation environments that might hinder biological development. The outer regions have fewer heavy elements needed for planet formation and technology. The galactic habitable zone, a region with conditions favorable for life, provides a natural focus for surveys. Webb sensitivity enables examining stars throughout this zone and comparing properties across different galactic environments. Multiple independent detections would provide the strongest evidence. Finding one anomalous infrared source is interesting. Finding 10 that all share similar properties across different stars becomes compelling. Finding 100 would be nearly impossible to explain through natural processes. Building that statistical case requires systematic surveys and consistent analysis methods applied across large samples. The null result carries information too. If we surveyed 10,000 sun-like stars within 1,000 light-years and find no convincing Dyson Sphere candidates, that tells us something about the frequency of advanced civilizations in our galaxy. Either they're rarer than we hoped, or they don't build these structures, or they exist but use different technologies we haven't thought to look for. Each possibility has implications for understanding life's place in the universe. Verification protocols for potential detections involve multiple steps. First, detection flags an anomaly in the data. Initial analysis rules out obvious instrumental artifacts and data processing errors. Follow-up observations with the same instrument confirm the signal persists. Observations with different instruments verify the detection isn't specific to one telescope or detector. Multiple teams independently analyze the data to ensure the anomaly isn't an analysis error. Only after clearing all these hurdles do you start seriously considering artificial origins. The bar for claiming detection of artificial structures is extraordinarily high. Natural explanations always get priority until they're exhaustively eliminated. The history of astronomy includes many anomalies that turned out to have mundane explanations once better data became available. Pulsars were briefly considered possible alien beacons. Fast radio bursts generated speculation about artificial origins. In every case, natural explanations eventually prevailed. That pattern teaches caution about jumping to artificial conclusions. But caution doesn't mean dismissing the possibility. Webb's capabilities enable asking questions that couldn't be addressed before. The search continues with better tools, refined methods, and growing datasets. Somewhere in the accumulating observations might be the signature we're looking for, or confirmation that such structures don't exist in our cosmic neighborhood. Either answer advances our understanding. The detection process itself involves layers of complexity beyond simply pointing a telescope and looking. Webb doesn't take traditional photographs. It collects photons across specific wavelength bands, building up spectral energy distributions for each object in its field of view. these distributions reveal how much light an object emits at different infrared wavelengths. A normal star shows a pattern determined by its surface temperature. Hot stars peak at shorter wavelengths. Cool stars peak at longer wavelengths. Physics dictates these relationships precisely. A Dyson sphere breaks those patterns. The star's energy gets absorbed and re-emitted at cooler temperatures. The spectrum shows excess infrared radiation that doesn't match what the star should produce naturally. But identifying that excess requires knowing what the star would look like without the structure. That means determining the star's fundamental properties from whatever light isn't blocked. Spectroscopic analysis provides those clues. Absorption lines in the spectrum reveal which elements exist in the star's atmosphere and in what quantities. Those chemical fingerprints constrain the star's temperature, age, and evolutionary state. Models predict what the complete spectrum should look like. Any deviation from that prediction becomes interesting. The challenge lies in distinguishing artificial structures from natural phenomena that also produce infrared excess. Young stars are surrounded by protoplanetary disks of gas and dust that glow in infrared. But these disks have characteristic spectral features from silicate dust grains and organic molecules. They also show variability as material spirals inward. Dyson spheres shouldn't show those same features or that same behavior. Debris disks around mature stars produce infrared excess too. When asteroids collide or comets disintegrate, they create dust that absorbs starlight and re-radiates it. But debris disks are typically thin and patchy, not the uniform shells that complete Dyson spheres would create. The spectral signature differs because the dust is distributed differently and the temperatures span a wider range. Evolved stars in late stages of their lives sometimes eject material that forms dusty envelopes. Red giants and asymptotic giant branch stars create shells of gas and dust that glow brightly in infrared. But these objects have distinctive spectral features, and the central star shows signs of advanced age. They're also relatively rare and easy to identify through their unusual properties. Ruling out each natural explanation requires careful analysis of multiple properties simultaneously. Is the infrared excess consistent with dust grain properties? Does the spectrum show features expected from natural dust? Is the star's age compatible with disk formation? Does the light vary in ways that suggest orbiting debris? Only when all natural explanations fail does the artificial hypothesis become worth serious consideration. Machine learning algorithms help sift through massive datasets looking for anomalies. You train neural networks on examples of normal stars, stars with protoplanetary disks, stars with debris disks, and evolved stars with shells. The algorithm learns what each category looks like in terms of spectral properties, brightness variations, and other characteristics. Then you feed it new observations and let it flag anything that doesn't fit the known categories. This approach scales to analyzing millions of stars systematically. Human astronomers can't manually examine every spectrum from every star in a large survey. Algorithms can, highlighting the most interesting candidates for detailed follow-up. But algorithms also make mistakes, flagging instrumental artifacts or rare but natural objects as anomalies. Human verification remains essential. The statistical framework for evaluating detections involves Bayesian reasoning. You start with a prior probability that any given star hosts a Dyson sphere. That probability is extremely low given we've never confirmed one before. Then you update that probability based on the observations. How likely is the observed spectrum if a Dyson sphere exists? How likely is it under various natural explanations? The ratio of those likelihoods determines how much the observations shift your belief. Strong evidence requires the observations to be far more likely under the artificial hypothesis than under natural ones. That's a high bar to clear because natural explanations are numerous and well understood. You need observations that are virtually impossible to explain naturally but perfectly consistent with artificial structures. Multiple wavelength coverage strengthens the case. Webb operates in infrared, but visible light observations reveal the star's properties. Radio observations might detect emissions from power generation or communication. X-ray observations could show activity related to energy collection. Concordance across multiple wavelengths builds confidence that you're seeing something real rather than an artifact of one instrument. Time domain astronomy adds another dimension. Watching objects over weeks, months, or years reveals whether their properties change. Natural disks evolve on observable timescales as material accretes or disperses. Artificial structures might show different variability patterns related to construction activity or operational changes. Or they might remain remarkably stable if the structure is complete and in equilibrium. Coordination between space-based and ground-based observatories maximizes coverage. Webb provides unparalleled infrared sensitivity but limited observing time. Ground-based telescopes offer more flexibility and can monitor objects continuously when weather permits. Radio telescopes cover wavelengths Webb can't access. Combining data from multiple facilities creates a more complete picture. International collaboration ensures independent verification. When one team claims a detection, others need access to the data and the ability to perform independent analyses. Scientific journals require this transparency before publication. The discovery of something as significant as artificial structures would trigger immediate scrutiny from the global astronomical community. False positives are inevitable in any search. With millions of stars surveyed, some will show unusual properties purely by chance. Statistical fluctuations, rare natural phenomena, and instrumental quirks create noise in the data. The key is designing search strategies that minimize false positives while remaining sensitive to genuine detections. Setting detection thresholds involves balancing sensitivity and specificity. Lower thresholds catch more potential candidates but generate more false positives. Higher thresholds reduce false positives but risk missing real detections. The optimal threshold depends on the costs of each type of error and the underlying frequency of what you're searching for. Blind analysis techniques reduce bias. Analysts examining data don't know which objects are genuine candidates and which are control samples until after they've completed their analysis. This prevents unconscious bias from influencing judgments about ambiguous cases. Only after finalizing the analysis methods do you reveal which objects are which. The search strategy evolves as observations accumulate. Early results inform where to look next. If initial surveys find no candidates around Sun-like stars, you might expand to other stellar types. If you find candidates that turn out to be a new class of natural objects, you learn how to better distinguish those from artificial structures. Negative results have scientific value. If systematic surveys of thousands of nearby stars find nothing, that constrains how common Dyson spheres can be. Either advanced civilizations are extremely rare, or they don't build these structures, or we fundamentally misunderstand what they would look like. Each possibility teaches us something about the universe. The search also drives technological development. Methods created for finding Dyson spheres improve our ability to characterize exoplanets, study stellar evolution, and understand dust in space. Even if we never find artificial structures, the techniques developed in the search advance astronomy broadly. Public interest in the search generates support for space science. People find the possibility of detecting alien megastructures exciting even if the probability is low. That excitement translates into support for missions and telescopes that enable these searches. The search for techno-signatures becomes a gateway for broader engagement with astronomy. Educational opportunities emerge from the search. Students learn about stellar physics, infrared astronomy, data analysis, and the scientific method through involvement in surveys. Whether or not we find anything, training the next generation of astronomers happens through hands-on participation in real research. Philosophical implications loom behind the technical details. Finding evidence of artificial structures would fundamentally alter humanity's understanding of its place in the universe. We would know definitively that advanced technological civilizations exist beyond Earth. That knowledge would raise immediate questions about why we haven't detected other signs of their presence and whether contact is possible or desirable. The Fermi Paradox gains new dimensions if we find evidence of structures but no communication. Why would a civilization capable of building Dyson spheres not be broadcasting or responding to our signals? Are they uninterested in contact? Are they extinct but their structures remain? Are they so advanced that communication with us seems pointless? Each possibility suggests different futures for our own civilization. Alternatively, finding no evidence after extensive searches sharpens the paradox. If the galaxy is old and large, and if life emerges readily, where are the megastructures? The Great Filter concept suggests some barrier prevents civilizations from reaching this level. Is the filter behind us or ahead of us? The answer has profound implications for humanity's long-term prospects. The search continues regardless of results. Each new observation adds data points. Each refined analysis method improves our ability to distinguish artificial from natural. Each telescope upgrade extends our reach. Somewhere in the accumulating evidence might lie the answer to whether we're alone or whether others have reshaped their solar systems on scales we're only beginning to imagine. The question remains open, but the tools to answer it grow more powerful with each passing year. The timeline for detection depends on factors we can't fully control. Survey depth, available telescope time, and analysis resources all matter. A nearby Dyson sphere might appear in data we already have, waiting for the right analysis method. A distant one might require instruments not yet built. The possibility exists that we've already observed stars hosting partial structures but classified them as natural phenomena. Our catalogs contain millions of objects. Systematic reanalysis with new criteria could reveal candidates hiding in plain sight. This has happened before in astronomy. Pulsars were detected years before anyone recognized what they were. The first exoplanet data existed in archives before the discovery was confirmed. Collaboration between professional astronomers and citizen scientists expands search capacity. Projects like Galaxy Zoo demonstrated that distributed human pattern recognition can process vast datasets. Similar approaches applied to infrared surveys could identify unusual objects that automated algorithms miss. Thousands of eyes examining data spots anomalies that might otherwise go unnoticed. Machine learning offers complementary capabilities. Neural networks trained on known astronomical objects can flag outliers that don't match any established category. These outliers become candidates for closer examination. The combination of human intuition and algorithmic processing creates a powerful search methodology. International cooperation amplifies search effectiveness. Different nations operate different telescopes with different capabilities. Coordinated observation campaigns provide multiple perspectives on candidate objects. What appears ambiguous in one wavelength might resolve clearly in another. What one observatory sees at one time might change when another observatory views it months later. Global networks of astronomers sharing data and analysis methods accelerate the pace of discovery. The economics of the search favor patient, systematic approaches. Unlike missions to distant stars, searching for Dyson spheres costs relatively little. Most observations use existing telescopes during time already allocated for other surveys. Analysis happens on standard computers. The search piggybacks on infrastructure built for other purposes. This efficiency means searches can continue for decades without massive budgets. Persistence becomes feasible in ways it wouldn't be for more expensive endeavors. Cultural factors influence how we interpret potential discoveries. Different societies might view evidence of alien megastructures through different philosophical lenses. Some might see it as validation of technological progress as a universal path. Others might question whether our own trajectory toward large-scale engineering projects serves our long-term interests. The discovery would spark debates about humanity's future that transcend the scientific details. These conversations have value regardless of whether we ever find anything. The search methodology continues evolving as our understanding deepens. Early proposals focused on complete Dyson spheres around single stars. Modern searches consider partial structures, swarms of independent collectors, and constructions around binary systems or unusual stellar types. The possibility space expands as we think more creatively about what advanced civilizations might actually build. Perhaps they prioritize energy capture around pulsars for their stable output. Perhaps they build in stellar nurseries where raw materials are abundant. Perhaps they avoid main sequence stars entirely and focus on white dwarfs or brown dwarfs. Each variation requires different search strategies and produces different observational signatures. The role of serendipity cannot be ignored. Many astronomical discoveries happen by accident when observers notice something unexpected. Someone analyzing data for an unrelated project might spot an infrared excess that doesn't fit any model. Someone testing a new instrument might find an unusual object in a calibration field. The history of astronomy suggests that staying alert to anomalies matters as much as systematic surveys. Both approaches complement each other. Philosophical preparation for discovery seems prudent even if the probability remains low. How would humanity respond to definitive evidence of alien megastructures? Would it unite us around a shared sense of cosmic context? Would it fragment us as different groups interpret the implications differently? Would it change our priorities regarding space exploration, resource allocation, or long-term planning? Thinking through these scenarios before they occur helps us respond thoughtfully rather than reactively. The absence of evidence also carries meaning. If we conduct thorough searches of thousands of nearby stars across multiple wavelengths and find nothing, that null result constrains the prevalence of Dyson spheres. Either they're extraordinarily rare, or advanced civilizations don't build them, or we fundamentally misunderstand what they would look like. Each conclusion teaches us something. The first suggests life rarely reaches advanced technological stages. The second suggests technological development doesn't inevitably lead to massive energy infrastructure. The third suggests our assumptions about alien engineering need revision. All three possibilities reshape how we think about our future. The relationship between Dyson spheres and other technosignatures deserves consideration. If a civilization builds structures to capture stellar output, they probably also produce other detectable signatures. Radio transmissions, optical lasers, atmospheric pollution on their planets, or heat from their computational infrastructure might all be detectable. A comprehensive search strategy looks for multiple signatures simultaneously. Finding one type increases the probability of finding others. The searches reinforce each other. Time scales matter profoundly in this search. Human technological civilization has existed for centuries, but systematic astronomy with modern instruments spans only decades. The universe has existed for billions of years. If Dyson spheres exist, they might be built by civilizations millions of years old. The structures themselves might outlast their builders by eons. We might be searching for artifacts of extinct civilizations rather than active ones. That possibility adds poignancy to the search. We might find evidence of greatness long vanished, structures still orbiting stars whose builders disappeared before Earth formed. The search connects to deeper questions about the nature of intelligence and technology. Is large-scale engineering an inevitable outcome of advanced intelligence? Or does intelligence mature beyond the need for physical structures, finding more efficient ways to process information or exist? Perhaps truly advanced civilizations transcend physical form entirely and leave no structures behind. Perhaps they build in ways we can't detect because their methods operate on principles we haven't discovered. These speculations remind us that our search assumptions reflect our current understanding, which might be incomplete. The search for Dyson spheres becomes a mirror reflecting what we might become if we navigate our current filters successfully. We look for evidence of others who survived their technological adolescence and graduated to stellar-scale engineering. In searching for them, we're really asking whether that path exists, whether it's achievable, whether intelligence anywhere ever figures out how to persist long enough to reshape solar systems. The 17 stars wait in the darkness, their light traveling toward us carrying information we're only beginning to decode. Webb waits at L2, its instruments cold and sensitive, ready to collect the photons that will tell us what those stars really are. Astronomers wait at their computers, preparing analysis pipelines and verification protocols for whatever the data reveals. And humanity waits, perhaps without fully realizing it, for an answer to a question we've been asking since we first looked up and wondered if anyone else was looking back. The answer is coming. Not today. Not tomorrow. But soon, on timescales that matter to science if not to individual lives. The data accumulates. The picture clarifies. The universe prepares to tell us something we've wanted to know since we became capable of asking. And when that answer arrives, whether it confirms our hope or our solitude, we'll have earned it through careful observation, rigorous analysis, and the patient application of scientific method to the oldest question our species has ever asked. That's worth something regardless of what the answer turns out to be,